Let us start. Yesterday, we have done a new type of problems having two beams, AB and BC, which is being joined here at the point B here by means of a frictionless hinge. So, one of these beam is loaded by an amount, loaded by one of this beam AB is loaded by a triangularly distributed load of intensity 0 at the end B and 9A at the end A, and the next beam BC is loaded by an amount by a torque 30 kilonewton at the point T, which is away from the end B by 6 meters. Now, end AB is being supported at the end A, and the beam BC is supported by cantilever support at the end C. Now, we have gone through the load diagram, which is supposed to be introduced here. There is no bending moment at the hinge joint at P. Instead, it is supported, although it is supported at the end P, there is no vertical moment, vertical force, or there is no vertical moment. Actually, this is hinge joint is being acts as a support, but it is not creating any reaction anywhere. So what happens? If you take the bending moment, now if you take the bending moment from the point A to the left portion, that is the AB portion of the beam, that is AB portion of the beam, then the reaction RA will be multiplied by 10 is equal to, that is equal to 10 into 9, which is half of the bending moment, half of the area, which is the intensity is equal to 9, half multiplied by a triangular loading, which is half multiplied by the base multiplied by the height, where you can say the base is equal to 10 and height is equal to 9. So half 10 into 9 is the loading on the left side, and it is it is reflected by an amount 2/3 of the length L. It is acting at a length, say around 2/3 from this end. At the 2/3 from this end, so it will be 2/3 of the just 1 second. Just a second. Yes. So what is going on here? It is I'm erasing it and doing it again. No, this force is supposed to be acting at a distance 2/3 from the end P. So it has become the 10 multiplied by 2/3, that is equal to 30, and RA is equal to 30 kilonewton, or RA is equal to 30 kilonewton. And RC, the load at the end B, will be the 10 multiplied by 2, 10 into 10 into 9 by 2, by loading at this end, loading acting on this side, that is the 9 half into 9 multiplied by the length 10 multiplied with, and the clockwise moment, it is giving anti-clockwise moment, and a now this is giving a clockwise moment if we take the moment about C, and no and 30 kilonewton. Okay, at C 10 into multiplied by if we take the vertical loading, so it will be RC is equal to 10 to 9 divided by 2, the half multiplied by the making clockwise moment, and multiplied by minus 30. There is a couple here, which is coming into picture here. Minus 30 is equal to 15 kilonewton. Now, the shear force diagram, we have already discussed the shear force diagram here. Let us do the bending moment diagram. Now, let the portion AB x from the end B, the portion AB x from the end P is mx is equal to, we take the distance x here, that is the portion from here to here, that is mx is equal to 15x, that is the loading here, 15 into x multiplied by 0.15 x cube, or MB at the point B is equal to 0, and MD at the point at MA is equal to, where x is equal to 10 is also equal to 0. The maximum bending moment will be at x is equal to 5 by 3. As we know, the shear force is 0 at x is equal to 5.77. So at the point of 0 shear stress, the bending moment will be maximum. That is 15 into 5.77 multiplied 0.15 into 5.77 to the power 3 divided by 2 is equal to 72.1 kilonewton per meter. As bending moment at B is 0, then the part BC may be assumed as the as a cantilever. So the portion BD from here, from x to B, then take the value of x from here, then mx will be equal to minus 15 into x. And B is equal to x is equal to 0 is equal to 0, and MB is equal to 6 is equal to 6, that is equal to minus 90. If you put the value of x is equal to 6, the portion from DC from x is equal to DC, then mx is equal to minus 15x minus 30 DC. Minus 15x minus 30. So in that case, that is MD at x is equal to 0 is 120, MD, MC at x is equal to 10, means right end, that is minus 180 kilonewton per minute. To check the taking moment of all the forces about the C, we can have 30 into 20 minus 45 into 10 plus 230 into 10 plus 30 to 120 kilonewton. So this gives us the bending moment diagram here. Now let us go through another type of problem. In case the inclined loads, in case the loads on the beam are inclined, are not perpendicular to the axis of the beam, the loading can be resolved axially and transferred to the beam. Here the loading is not perpendicular to the axis of the beam, means it is an angle with the axis of the beam. This loading can be resolved axially, means along the axis of the beam and across the axis of the beam. The transverse component of the load produces shear forces. This load across the axis or transverse component produces shear force or force vertical to the longitudinal axis of the beam, and bending moment, where the axial moment produces a push or pull. This reaction, horizontal reaction, is taken by the hinge support only as a roller supports are unable to do so. This we have to taken by means of a hinge support at one end like this here, while the roller support, it cannot keep the beam in a steady position. Say a 10-meter long horizontal beam is loaded as in the figure 4.41. Draw the axial force, shear force, and the bending moment diagram here. And 10-meter long horizontal. Okay. What we have here, we have one force to 2 kilonewton, which is at an angle 45 degree with the longitudinal axis of the beam, and that 1 K, which is 45 degree with the angle axis of the beam, and 3 K at 30 degree at the axis of the beam. So what we have to do here, very simple. We have to make the reaction again in the RA and RB, and the load components is shown here in the 2 kilonewton 45 degree angle with 45 degree angle, 1 kilonewton with 45 degree angle in opposite direction, 3 kilonewton 30 degree angle but in opposite direction. The point 3, C, D, and E is shown from the left hand as with the distance 2 meter, 2 meter, 3 meter, and 3 meter. It is supported at right end at B, and it is supported by a hinge. It is simply supported at the right end. Right end means at B point the P, and the beam is supported by a hinge at the left end A, as it has inclined beam, and it has inclined loading, and all these inclined loads have a horizontal component which will make the beam move unless it is hinged at one end. So the support, the force reaction is the load diagram is shown here. At this here, we have RA with the hinge joint. This only A reaction at A at the vertical direction, at B reaction at the vertical direction, and that's 45 degree angle as the load is at C. So if we resolve it in 2 kilonewton multiplied by cos 45 degree, we'll have 1414 Newton in the horizontal direction and 1414 Newton in the vertical direction. And in 1 kilonewton, we have the same 707 in the horizontal direction leftwise, 707 vertical direction downwards. And 3 kilonewtons with cos 30 degree will be 2598 Newton leftwise, and vertical component 1500 Newton vertical downwards. This is the force diagram here. Now, if we take the moments about the hinge A, then RB at the hinge A means this point, then RB will be RB multiplied by the distance 10, 2 plus 2, 4 plus 3, 7 plus 3, 10 meter. So this is RB multiplied by 10, which is equal to the moments of the vertical forces on vertical components of the forces only. That is 1412 multiplied by 2 means this here 707 multiplied by 4 here, and 1500 multiplied by 2 plus 2 plus 3, that is 7 here. So RB become 1615.6 Newton, and RA become 1414 plus 707 plus 1500 is RA become, we'll take the vertical forces only. The vertical forces RA will be upwards and RB will be upwards. So it is taken on the right side of the equal to sign. So this for RA plus RB will be positive and others will be negative. Means the Newton 1414, 707 and 1500. This will be negative with negative sign. If we put it at the left side of the equal to sign and we put it right of this equal to sign, these three will be positive, and 161 15.6, that is RA, part B will be negative. So as a whole, RA will become 2005.4 Newton. So the two horizontal load on the beam will be 1417 minus 707 minus 2598 is equal to minus 1891 Newton acting leftwards. Thus, the roller support does not provide any horizontal reaction. So roller reaction in the hinge support is only the horizontal reaction, and the hinge support will be just opposite 1891. So the horizontal reaction is on the hinge support, and it is producing exactly equal and opposite reaction, that is equal to 1891 Newton. Now shear force diagram will follow the same way as A to B. We have two vertical forces. One is 1/4 upwards, and if we take a section somewhere here, take a section here at a distance x from this end, this reaction, there will be only one vertical force acting on this direction, that is the reaction RA 1414. That is equal to the shear stress at this position, the shear force at this position. AC. That is that is only 2005 RA into 2005.4 RA. That is only the vertical force acting over this direction. So that is equal given here 2005 RA up to the end, that is equal to B, that is equal to C. Next, after the point C, if you take the section here, we have to take this section X here. Take the section X here. There we have two vertical forces. One is the RA 2005 acting forwards, this is positive, and another vertical forces 1414 Newton, which is acting downwards, which is negative in nature. So difference between the two will give us the shear force 591.4 acting between the point C and D. And if we take the section here like this, at a distance x. Now we have vertical force RA, that is 2005.4, one vertical force downwards 1414, and another vertical force 707 downwards, that is negative. Means 141 will be negative and 707 will be negative, and 2005 will be positive. So this equation will produce create a shear force 115.6 Newton up to the point T. Next, if we take the section again here like this, and X is here, X is here. So we have vertical forces acting upwards RA, that is 2005.4, one vertical force 1414, 707, another 500 Newton, all are acting downwards. So there's one force acting upwards and three forces acting downwards will create the total force, shear force, equal to 1615.60 acting downwards. So this will be the shear force diagram. This portion is positive and this portion will be negative. Now, The bending moment diagram will follow in the same manner. Again, you have to follow the same procedure for creating the bending moment. Say, again, you are taking the force here, section here, that is equal to X. Now, there is only one force acting from the section A to X, that is RA, which is equal to 200.5.4, and the moment it will create will be the distance from the section X, that is multiplied by X. So 200.5 multiplied by X will be the bending moment here, and it will be equal to 0 at A, and it will be equal to it will multiply by 2, then it will be equal to 4010.8 Newton meter at the point C. And now, if we take the bending moment, if we take the bending moment again in another section here, like this, say here, at a distance X from the end A, then this distance from A to C is 2 meters. So one force is acting RA at a distance X, at RA acting, which is creating clockwise moment, that is positive. Another force is 1414, which is acting X minus 2 meters from the section X. So that will get negative bending moment 1414 into multiplied by X minus 2. This will become, thus this becomes 14205.4x minus 1412 into x minus 2. At the moment C, where x is equal to 0, this force will become bending moment equal to 1410, and at x is equal to 4, 5193, which is shown here, like here. 5193, this is 5193. Next, if we take section here, somewhere here, let the section X is the point is X. So distance of this force is X minus 4. This is X minus 2. And this force is X. So if you take the moment accordingly, this will create anti-clockwise movement, which is positive. This will create anti-clockwise moment, and this will be multiplied by x minus 2. And this will create anti-clockwise moment multiplied by x minus 707 multiplied by x minus 4. So this moment will be like this. Here, the bending moment diagram will become DE, that is 205.4x minus 1414 into x by 2 minus 707 x minus 4. Thus, at t is equal to 4, bending moment will be 5193.6 when x is equal to 4. At t is equal to e, when x is equal to 7, bending moment will be 1846.8 Newton meter. Next, the portion EB. Next, the portion EB. Here, we follow the same procedure. That is X. So distance of line of action, distance of the line of action of 1500 Newton is equal to X minus 2 plus 2, 4 plus 3, 7. And that of 707, x minus 4. And that of 14114 is equal to x minus 2. And that of 1414 here is equal to x. So if you multiply it accordingly, since RA 1414, this force 1414 Newton, 707 Newton, and 1500 Newton, all are creating anti-clockwise moment. So they create negative bending moment, and 1414 N is creating clockwise moment, it became positive bending moment. So bending moment diagram will be like this, which is given. Bending moment equation will be like this. 2005.4 x minus 1414 x minus 2 minus 707 x minus 4 minus 5000 x minus 7. So ME at x is equal to 7 become 74846.8, and MB at x is equal to 9 is equal to 0. So bending moment diagram will thus becomes will take particular with this particular shape. Now the shear force or thrust diagram, the thrust diagram will be like this. The thrust between A to C is equal to 1891. That between C to D, that is equal to 3305, and that becomes C to D becomes 3594. So this will be, in fact, this is the thrust diagram given here. So this figure, last figure shows us the thrust diagram. Okay, with this, I am finishing this module, shear force and bending moment diagram. And let us go for the next portion, next chapter, that is the bending stresses. Bending stresses in the beam. Just 1 second. If a member is subjected to, what is the bending stresses in the beam? Now, what we have seen, what is a beam? A beam is a prismatic bar subjected to loading normal to its longitudinal axis. Now, if a bend is subject to equal opposite couples acting in the same longitudinal planes, the member is said to be peer bending. So, equal and opposite couples means if we equal an opposite bending moment acting in the same longitudinal plane, the member is said to be in pure bending. So, there is supposed to be a one bending moment of which is acting clockwise direction like this, and another bending moment which is acting anti-clockwise direction like this. Both these bending moment have the same value. So if these two bending moment exist over a same longitudinal axis, then you will try to bend the beam. The member is said to be under pure bending, or beam is trying. These couples are bending the beam. If a constant bending moment no shear force acts on some length of the trees, the stresses set up on any section on that part of the beam constitute a pure couple, and the magnitude of which is equal to the bending moment. Though the stresses set up on that part of the beam constitutes a pure couple, the magnitude of the equal to the bending moment. This couple is supposed to be equal to the bending moment, which is creating the stresses in the beam. The internal stresses created developed in the beam as known as flexural or bending stresses. So the stresses due to the stresses created due to the bending of the beam is called bending stresses or called flexural stresses. And the figure a portion CD of the simply supported beam is under pure bending, as there exists no shear force such. The figure 5.1 is shown here. The portion CD means here from here to here of the simple supported beam is under pure bending, as there exists no other shear force, means there is no vertical force acting on this area of the beam. So the bending is under TB is under pure bending, as there is exists no shear stresses. Now, if the end of the beam, if the end sections of the straight beam are considered to be remain plane, the beam under the action of bending moment bends in such a way that the inner or the concave portion of the cross section undergoes compression, and outer of the convex edge remains tension. So the bending beam under action of bending forces will bend in such a way the inner or concave edge undergoes compression, and outer of the convex edge undergoes tension. Inner or concave edge undergoes compression, outer and the convex edge undergoes tension. There is an intermediate surface known as neutral surface. That is where there is no tension and no compression. There is which is known as neutral surface, in which the stress is zero, means there is no tension or no compression. An axis obtained by intersection of the neutral surface and a cross section known as neutral axis. An axis obtained by the intersection of the neutral surface and a cross section is defined as neutral axis about that bending of the surface takes, about which the bending of the surface takes place. For any cross section, the intersection of the bending surface, neutral surface, and this cross section is defined as neutral axis about which bending of the entire surface takes place. So what is said? If the beam bends in this way, means concave at the top side and convex at the bottom side, the top side will be under compression, bending, and the bottom side will be under tension. And there exists a surface side which does not subjected to any tension or compression. This is defined as the neutral axis. The following theory is applicable to the beam subjected to pure or simple or pure bending. When the cross section is subjected to shear force or since there will cause a distortion of the transverse plate. Now, there are few theories of simple bending. This is applicable to the beam subject to simple or pure bending when the cross section are not subject to shear force, since they will cause a distortion of the transverse plate. The assumptions being made as like this: the material is totally homogeneous and isotropic. That is, it has same sorry, it has same values of shear Young's modulus in tension and compression. Material is homogeneous, isotropic. It has the same values of Young's modulus in tension and compression. The transverse planes remains plane and perpendicular to the neutral surface after bending. Transverse planes remains plane and it is perpendicular to the neutral surface after bending. Means all the cross sections remains plane and it is perpendicular with the neutral surface after bending. Initially, the beam is straight and all longitudinal filaments are bent into circular arcs with a common center of curvature, which is large compared to the dimension of the cross section. So all the beam is straight initially. All the longitudinal filaments are now bent into circular arcs with a common center of curvature. Then, due to the bending, all longitudinal filaments are bent into circular arcs, are not elliptical or any other formation, but with a common center of curvature, which has this circular arcs has a center which is common for all the arcs, for all the fibers, and this which is large compared to the dimension of the cross section. This radius of curvature, center of curvature, and radius of curvature is large compared to the dimension of the cross section. The bend is symmetrical about a vertical longitudinal plane. Beam is symmetrical about a vertical longitudinal plane passing through the vertical axis of symmetry for longitudinal beams. The stress is purely longitudinal and the stress concentration effects is purely longitudinal. The stress and concentration effects near the concentrated loads are neglected. So always all these stresses are longitudinal stresses. The stress concentration effects near the concentrated loads are all neglected. Now, what you are doing here, consider a beam of under the action of a bending moment M. This is the beam, and it is subject to the understood bending moment M. Now, Nn is the original length. Nn is the original length considered to the beam. The neutral axis before the bending. The neutral axis is the plane through which axis, through the axis. Neutral axis means the axis doesn't have any tension and compression, is passing through the axis or the cross section, central cross section. In this side view NA, in this side view NN, in this side view, the cross section, this neutral axis or NA integrates the neutral axis. O is the central of curvature of the center of curvature bending. It's like this. So upper portion of the will be under bending stresses and lower portion will be under tensile stresses. Then from O, now R is the radius of the surface of the central axis. So of the neutral surface. So from here O to the value R, this is the neutral axis. This is the neutral axis now. And theta is the angle separated with the beam length at center O. So this is the arbitrary length of the beam we have taken into consideration, and this beam is creating an angle theta separated with the center O. And sigma is the longitudinal stress introduced here. A filament of long length, a filament of original length Nn, which is here, at a distance y for the neutral axis be elongated by length by the amount AB. So NN, which was in original length in this direction, it is now elongated from to the surface up to this point AB. Now the strain in AB minus NN divided by the original length NN. The original length of filament is supposed to be NN. So sigma by E, the R into Y, R plus Y into theta minus RY divided by RY, R into theta. R into theta is the length of the original NN, and R plus Y into, which is elongated after the bending, multiplied by theta is equal minus RY is equal by RY. So this will become sigma by E is equal to Y divided by R, or sigma by Y is equal to E by R. Also sigma is equal to Y into E divided by R into, or more or less is proportional to Y, as E by R is constant. This stress is proportional to the distance from the neutral axis, and thus